Hello students, welcome to this video. Chapter 3, Linear Programming using computer solution. We're going to use Excel to help us go through this process, and we will be doing some sensitivity analysis, which basically means if we start changing some of the components of the model, what happens. So the example we're going to go through is the Beaver Creek pottery example from Chapter 2, where we are trying to maximize our profits. Profits for each bowl we produce is $40, 40x1, and for each mug it's 50x2, subject to two constraints. The first constraint is a labor constraint, so mugs take twice as long. So we have x1 plus 2x2 is less than 40. We only have 40 hours of labor available, and then the amount of clay that we have. It looks like bowls take more clay than mugs do, so we have 4x1 plus 3x2 is less than equal to 120. And as always, we have the non-negativity constraints that both x1 and x2 have to be greater than 0. We're going to be solve using Excel. We're going to determine the optimal solution. Then we will play around with some of the variables to see what happens when we make a change to the final solution. That's the sensitivity analysis that we'll be going through. What happens if the coefficients for the objective functions are changed? Remember that the objective function is right in here, the 40x1. Oops, I don't need any of that. 40x1 plus 50x2, that's the objective function. And then we are also, what happens if the coefficients to the constraint variables are changed? What happens if the right-hand side of the constraints are changed? So the right-hand side being 40 and 120, what happens if the coefficients for x1 and x2 in the constraints are changed as well? So we're going to use Excel to help us through this. I have this template available for you. We're going to use this here. It uses a solver, so you may have to go in to File, Options, Add-ins, click Go at the bottom, and make sure you have a solver add-in. Click OK, and under the Data tab you'll have this solver tool. So what we're going to do, we're going to set this up to enable Excel to find the solution without us having to graph the solution. So the coefficients for the objective function, we have $40 and we have $50 there, subject to, I'm just going to write in here, labor and clay as our constraints, just to keep these straight. They're subject to 1 and 2, and I forget the rest. Let's go back here. Let's bring that over there and this here for a second. We have 40 hours. So we put in for the constraint sign less than and equal to. And then for here we're going to put 4 and 3 given those are the coefficients for the two variables for the second constraint. And we have available 120 units. Now there's formulas created in the usage column and in the leftover column, as well as in the profit or cost, this cell for B12. So we're going to leave those formulas alone. Next thing we want to do is go into Data, Solver. We're going to set this up. Let's reset all so we can kind of walk through this. So we're going to set the objective function. We're going to set that objective function by we want to maximize cell B12 in this case, wherever that profit cost is. And it's a maximization question by changing the variables for x1 and x2 right there. If we have x3 and x4, we'd just have to add cells or rows to include the other variables that we have. Subject to the constraints. We have two constraints. They're listed right here. We have to add them in. The cell reference is basically the usage column. So for the first constraint in labor, it's going to be E6. We have to make sure these signs, inequality signs, are accurate. So it's less than the amount available in column G. So let's just go right there. We're going to add one more. Same thing for the clay. Oops. We're going to the usage value, E7, less than and equal to the value we have in G7. And we're going to click OK. Make unconstrained variables non-negative. Make sure that's checked off. And we are using a simplex linear programming model. We're now going to solve this. We're going to also want to highlight answer and sensitivity. So we click OK, and we get a couple more tabs opened up at the bottom. We have our answer and our sensitivity. But Excel, or the Excel solver, basically, I'll just highlight that. That's our answer right in here. Basically, we are producing 24 bowls and 8 mugs for a profit of $13.60. This is something that we did in chapter 2. We drew it out and we found the same solution. So let's go into our answer report and see what this tells us. Let's make this a little bigger. Basically, it tells us that our objective function is maximized at 1360. There's the final value for the variables, the bowls and the mugs, as well as this statement right in there. This is saying that those two constraints are binding. So the solution existed at the intersection of those two equations. All binding constraints are going to have a slack or surplus of 0. Remember, if the inequality is less than and equal to, it gives us a slack variable. If it is a greater than equal to sign, it'll give us a surplus variable. In Excel, this will be always labeled slack, but a surplus will show up as a negative number. So if this value here is 0, it means that the constraints are binding. And because we only have 2 constraints, pretty well guaranteed that those 2 constraints are going to be binding. We will look at another example that I'll produce, where we have more than 2 constraints, and then we can see that some are going to be binding and some will be non-binding. So that is where the key values on the answer sheet. The sensitivity report gives us some really good information as well. Here's our final value, basically our answer. But this tells us how much we can actually increase the objective function. We can basically, there's our objective function. Let's center that. We could increase it by adding another 26.666, decreasing it by 15, so going down from 40 to 25. With the second objective function, we could increase it by adding 30 to it, so a total of 80, or subtracting 20 to get a total of 30. So the first constraint could be anywhere from 25 to 66.666667. The second constraint could be anywhere from 30 to 80. Now what does that mean with the objective function? The objective function basically says that if we make a change in the original question where our profit now for bowls is not 40 but maybe 50, what will change and what won't change? The optimal solution of 24 and 8 will not change. The variables or the constraints that are binding or non-binding will not change. Because our profit has changed, our final profit, our total profit Z, will change. So let's take a look. We can do this here. Let's change this to 50. it's within the allowable distance, or within the allowable range. You can see that these values here changed, but we need to run this again just to make sure. So solver, nothing else has changed. These values are set on cells that haven't changed. So we can press solve. We don't need any answer report. We just need to click OK. And look, optimal solution of 24 and 8 did not change, but our profit changed. Our profit changed because our profit for X1 has gone up from 40 to 50. Now if we change this from perhaps 40 to the upper limit is 66.67, let's change it to 70, something outside of that allowable range. So this now is 70. See, Excel will just kind of calculate that, but this value here is not going to be correct. We run solver, we solve it, we click OK, and look, our optimal solution is now 30 X1s, or 30 bowls, 0 mugs, and there's our profit. So changes that are within the allowable range don't change the optimal solution. The binding, non-binding constraints, the actual solution of 24 and X, 24 and 8 in this case, but of course the variable, the objective function Z will change. So what happens to the right-hand side of the constraints? Remember, the right-hand side of the constraints are these values here, 40 and 120. I'm going to change this back to 40. I'm going to ignore those values there, but we're going to look at what happens if we change the right-hand side of constraint 1. Basically here, there's our values for constraint 1. And here is the allowable changes. So we can increase the right-hand side of constraint from 40 to 80. If we do that, what changes? The optimal solution, the binding constraints will still be binding. The non-binding constraints will still be binding. Z will be different. And because we're changing the slope of the constraint, the actual mixture of how many we're going to produce of X1 and X2 will also change. So let's go through this. We're going to change this up to maybe just 70. See what happens. Data, solver. We're just going to run. We're not going to do any type of report. And there is our solution, 6 and 32. Remember, we're changing the right-hand side of our constraint. So if we were to draw this out, the slope of that constraint would change, which means that the optimal point is going to change. But our our binding constraints are still binding. Our non-binding constraints are still non-binding. And because we only have 2, we can't really see that in here because both constraints are going to be binding. Now we can see that we changed it within the limits. We can take a difference. We can calculate the difference of it now versus before. Difference is 480, and we changed it from 40, so we changed it by 30 units. So let's divide it by 30. We get $16 in terms of an extra profit for every unit that we changed the first constraint by. $16. Let's look at our sensitivity report and look at that value right there. Let's make that yellow and bold and there. That is the shadow price. The shadow price tells us how much the optimal solution Z will change by if we were to change the right-hand side of a constraint. So you look at these two values here, 16 and 6. If we had one more unit of labor or one more unit of clay, where would you want to put? Say you had a choice between adding one more hour or adding one more pound of clay to our for our resources. We'd want to add more labor because it's going to have a greater effect on our total profit by adding $16 for every hour of labor versus $6 for every pound of clay.